Hello there, and welcome. I'm so glad you found your way here tonight. So let's begin at the beginning, or rather, at the place where beginning and ending blur together, where observation becomes a kind of time travel, and where every distant star you see in the night sky is actually a memory made of light. You might have heard that when we look at stars, we're seeing them as they were in the past. Perhaps you learned this in school, nodded along, and moved on with your day, but let's drift into what that actually means for a moment, because it's stranger and more beautiful than it might first appear. Light moves fast, extraordinarily fast. Each second, a photon of light travels about 300,000 kilometers through the emptiness of space. That's fast enough to circle the Earth 7.5 times in a single heartbeat. And yet, across the vast distances that separate stars and galaxies, even light has to journey for a very, very long time. When you look up at the moon on a clear night, the light reaching your eyes left the lunar surface about 1 1/3 seconds ago. It's recent enough that the moon is essentially where you see it. The sun is farther away. The warm sunlight touching your skin right now, the golden light streaming through your window in the morning, began its journey 8 minutes ago. 8 minutes isn't long. The sun you see is the sun as it was when you were making breakfast, checking your phone, beginning your day. But now imagine looking deeper. The nearest star system to our Sun, Alpha Centauri, is just over 4 light-years away. When you see that pinpoint of light in the southern sky, you're seeing it as it was 4 years ago. If something dramatic happened there today, we wouldn't know for 4 more years. The light carrying that information is still travelling through the dark, crossing the incomprehensible emptiness between stars on its way to us. And that's our closest stellar neighbour. Most of the stars you can see with your naked eye are dozens, hundreds, even thousands of light-years distant. When you look at the constellation Orion, the red giant star Betelgeuse you're seeing existed about 650 years ago, around the time of the Renaissance on Earth, when Leonardo da Vinci was not yet born. The light from that star has been travelling through space for longer than the United States has existed as a country, longer than the printing press, longer than most of the history we think of as modern. Right now, as you lie there, photons are arriving at Earth after journeys lasting longer than the entire history of humanity. Some began their journey before the first humans walked upright, before the continents drifted to their current positions, before the age of dinosaurs ended. These are photons from distant galaxies, ancient beyond easy comprehension, and we're only now learning to catch them and understand what they're telling us. The most distant galaxies ever observed appear to us as they were over 13 billion years ago, when the universe itself was young, still in its cosmic infancy, only a few 100 million years old. The James Webb Space Telescope, which we'll meet properly in a moment, has pushed our vision back to that early time, capturing light from galaxies that formed when the universe was barely 4 or 5% of its current age. Think about that for a moment. Let that settle. We are seeing light from a time before our solar system existed, before the Milky Way galaxy took its current spiral shape, before most of the stars that fill our night sky were born. And so, as we look deeper into space, we travel backward through time. But to see these ancient places, we needed to build something extraordinary. Instruments that can catch whispers of light from the dawn of everything. Let's meet one of them. Imagine trying to see a candle flame on the moon. Not a bonfire, not a searchlight, just a single candle, flickering in the lunar darkness, viewed from Earth with all the atmosphere and light pollution and distance between you and it. That's roughly the challenge the James Webb Space Telescope was designed to overcome. And somehow, against all odds, it succeeded. On Christmas Day in 2021, a rocket lifted off from French Guiana carrying the most complex and delicate scientific instrument humanity had ever sent into space. Folded inside the rocket's nose cone, wrapped like the most precious gift imaginable, was a telescope that would take 30 days to unfold itself, step by careful step, into its full form. Every deployment had to work perfectly. There were no second chances, no repair missions possible. It was a one-way journey to a destination almost 1.5 million kilometers from Earth. The James Webb Space Telescope, Webb as astronomers call it with affection, doesn't orbit Earth the way Hubble does. Instead, it settled into a special place called the second Lagrange point, or L2. where the gravitational pulls of the Earth and Sun balance in a way that allows the telescope to stay in a stable position with minimal fuel. Out there, far from Earth's reflected sunlight and infrared heat, Webb could finally open its golden eye to the universe, and what an eye it is. The primary mirror measures 6.5 meters across, composed of 18 hexagonal segments that fit together like a honeycomb made of gold. Each segment is coated with a microscopically thin layer of gold because gold reflects infrared light exceptionally well, and infrared is what Webb was built to see. The mirror segments can be adjusted individually, aligned with extraordinary precision, so that they work together as a single, perfect surface. When fully deployed, this mirror is nearly 3 times larger than Hubble's, gathering far more light, seeing far deeper into space and time. But size alone isn't what makes Webb special. It's the kind of light it observes. While Hubble sees mostly visible light, the same light our eyes detect, Webb sees in infrared wavelengths, which are longer than visible light and invisible to human eyes. Why does this matter? Because the universe itself is expanding, and as space stretches, the light travelling through it stretches too. Light from the most distant, most ancient galaxies has been stretched so much during its journey that by the time it reaches us, it's no longer visible light at all. It's become infrared, shifted into wavelengths that only instruments like Webb can detect. This stretching of light is called redshift, and it's one of the most important clues we have about cosmic distance and the universe's expansion. The farther away something is, the more its light has been stretched, the redder it appears. Webb was designed specifically to see this ancient stretched light, to catch photons that have been travelling for over 13 billion years, arriving exhausted and transformed, but still carrying information about the universe's youth. To do this kind of observation, Webb has to be extraordinarily cold. Its instruments operate at temperatures around -233 degrees Celsius, colder than the surface of Pluto, colder than interstellar space in many regions. This coldness is essential because infrared light is essentially heat radiation, and if the telescope itself were warm, it would blind its own instruments with its own heat signature. It would be like trying to see distant stars while pointing a flashlight at your eyes. So Webb carries a sun shield the size of a tennis court, a structure made of 5 ultra-thin layers that block heat and light from the sun, Earth and Moon. This shield creates a permanent shadow, where Webb's mirrors and instruments can stay cold enough to detect the faint infrared whispers from the edge of space and time. One side of the sun shield faces the sun and can reach temperatures of about 85 degrees Celsius, hot enough to boil water, while the other side, where the telescope lives, stays at those extraordinarily frigid temperatures needed for observation. And recently, in late 2025, Australian PhD students developed artificial intelligence software that corrected subtle electronic distortions in Webb's instruments, restoring crystal clear vision without needing any physical repairs. It's a reminder that even our most sophisticated tools continue to improve, continue to sharpen, revealing details we couldn't see before. With Webb's golden eye open to the cosmos, astronomers began to see things they never expected. Things that shouldn't exist. Things that challenge the very story we tell about how the universe grew from simplicity into complexity. In science, there are surprises that delight and surprises that unsettle. Webb's first deep observations brought both, wrapped together in tiny red dots scattered across images of the early universe. Let's drift into what astronomers found and why it matters. When cosmologists model the early universe, running vast computer simulations that track how matter clumped together after the Big Bang, they expect a certain pattern. The universe begins smooth, almost perfectly uniform, with matter spread evenly in all directions. Over time, gravity starts pulling denser regions together, small clumps form, then larger ones, growing gradually over hundreds of millions of years. The first galaxies should be small, chaotic, dim, barely beginning to organize themselves into coherent structures. They're cosmic toddlers, just learning to walk. But that's not what Webb saw. Instead, Webb discovered approximately 300 galaxies in the early universe that are far too bright, far too mature, far too organized to fit those models. These are galaxies appearing as they were over 13 billion years ago, when the universe was only 400 to 700 million years old. less than 5% of its current age, and yet they shine with the luminosity of galaxies that should have taken billions of years to develop. Professor Haojing Yan at the University of Missouri was among the first to identify these candidate galaxies, and his reaction, shared by many astronomers, was a mix of excitement and confusion. These galaxies don't just look a little more mature than expected, they look impossibly mature. They display apparent stellar populations that would require hundreds of millions of years to develop, time they simply shouldn't have had. It's like planting a seed and returning the next day to find a fully grown tree, complete with thick trunk, spreading branches, and autumn leaves already falling to the ground. Some of these early galaxies show heavy element abundances, carbon, oxygen, iron, that require multiple generations of stars to produce. Here's why that matters. The first stars in the universe were made almost entirely of hydrogen and helium, the simplest elements created in the Big Bang. When those stars died in supernova explosions, they scattered heavier elements into space, enriching the gas clouds that would form the next generation of stars. This process takes time, a lot of time. Each stellar generation lives, dies, and contributes to the cosmic chemical enrichment that makes planets, and eventually life, possible. But these distant galaxies appear to have gone through that entire cycle, multiple cycles even, when the universe barely had time for even one generation of stars to be born and die. The timeline doesn't fit. It's like opening a time capsule from early human history, expecting stone tools and simple shelters, and finding instead advanced architecture, written language, and complex art. Astronomers have informally started calling some of these objects universe breakers, and the name captures the tension perfectly. If these observations are correct, if these galaxies are truly as massive and mature as they appear, then something fundamental about our models of galaxy formation needs to change. The standard story we've been telling, about slow, gradual growth from simple to complex, might be missing a crucial chapter. There might be a fast track, an express lane, that allows certain galaxies under certain conditions to form with extraordinary speed and efficiency. One particularly intriguing subset of these discoveries are the little red dots, compact, extraordinarily bright objects that might be galaxies, or might be something entirely different. They could be primordial quasars, powered by supermassive black holes that somehow formed incredibly early and are now consuming matter at furious rates, outshining entire galaxies. Or they might be black hole stars, theoretical objects where a black hole forms inside a massive star, creating something that has never been observed before. There's a strange comfort in discovering the universe is more mysterious than we thought. It means we haven't figured everything out, that the cosmos still holds secrets worth uncovering. These impossibly bright galaxies remind us that knowledge isn't a destination but a journey, and every answer opens new questions, deeper mysteries waiting in the dark. But while we peer billions of years into the past, searching for the first galaxies at the edge of observable space, other mysteries are much, much closer. Visitors from other stars passing through our solar neighborhood right now, carrying stories from places we may never reach. For most of human history, we believed everything in our sky belonged to us. The planets orbiting in their predictable paths, the comets returning on schedule, the asteroids tumbling through the inner solar system, all of it born here, native to our sun's gravitational domain. We mapped these objects, calculated their orbits, understood them as part of our cosmic family. Then, in October 2017, we met our first confirmed visitor from another star, and everything changed. An astronomer named Robert Verick was reviewing images from the Pan-STARRS telescope in Hawaii when he noticed something unusual, an object moving through the solar system on a trajectory that made no sense for anything that belonged here. Its path was hyperbolic, which meant it wasn't bound to the sun's gravity. It was just passing through, moving too fast to be captured, arriving from somewhere in the constellation Lyra and heading back out into interstellar space. They named it Oumuamua, a Hawaiian word meaning scout, or messenger from the distant past. It was the first time humanity had detected an object that definitively came from another star system. Oumuamua was strange in almost every way. It was elongated, shaped roughly like a cigar or perhaps a pancake, tumbling end over end as it travelled. It was small, maybe 100 metres across at most, dark and reddish in colour, reflecting very little light. But the strangest thing about Oumuamua was how it moved. As it passed the Sun and began its journey back into deep space, astronomers noticed it was accelerating slightly, moving faster than gravity alone could explain. Comets do this all the time through a process called outgassing. When ice heats up and sublimates into gas, it creates a tiny rocket effect that pushes the comet along. But Oumuamua showed no visible tail, no obvious signs of outgassing. So what was pushing it? The question remains unanswered. Some scientists suggest it was outgassing after all, but with ices so exotic or sublimating so subtly that we couldn't detect the usual signatures. Others, including Dr. Avi Loeb at Harvard University, proposed something more provocative, that Oumuamua might be artificial, perhaps a light sail or probe sent by another civilization, pushed by sunlight the way Earth's proposed Breakthrough Starshot project plans to push tiny spacecraft to nearby stars. It's a controversial hypothesis, one that most astronomers find unlikely, but it's scientifically legitimate enough to warrant careful consideration rather than immediate dismissal. 2 years later, in August 2019, an amateur astronomer named Gennady Borisov discovered the second confirmed interstellar visitor using a telescope he built himself in Crimea. This object, designated 2I Borisov, was far more typical. A comet with a clear tail, actively outgassing, looking much like the comets born in our own solar system. Spectroscopic analysis revealed familiar compositions, carbon monoxide and water ice, materials we recognise. 2A Borisov was comforting in a way, proof that not every interstellar visitor needs to be mysterious. Sometimes a comet is just a comet, even if it travelled here from another star. Statistical models suggest that 1 or 2 interstellar objects pass through the inner solar system every year. Most of them we never see. They're small, dark, moving fast, and our telescopes can only monitor tiny fractions of the sky at any given time. For every Oumuamua or Borisov we detect, dozens or hundreds slip past unnoticed, silent travellers on journeys that began in planetary systems light years away. Imagine Earth as a small island in a vast ocean, and for generations islanders see only the birds they know, species that nest on familiar shores. Then one day a bird lands that has never been seen before, exhausted from crossing impossible distances, carrying pollen from flowers that don't grow anywhere nearby. That visitor proves the ocean is full of other islands, other ecosystems, other stories. Interstellar space is like a slow river carrying debris from distant shores, branches, seeds, occasionally something more interesting downstream past our cosmic neighbourhood. These visitors remind us that our solar system isn't isolated. It's part of a vast galactic ecosystem where matter, and potentially information, flows between stars. Every interstellar object is a messenger from places we'll likely never reach, carrying clues about planetary systems light years away. They're cosmic time capsules, and we're just learning to open them. And so, these travellers from other stars occasionally pass through our neighbourhood, most of them unnoticed. But one recent visitor has captured attention in ways the others didn't, not just because of where it came from, but because of how it moves. In July 2025, astronomers detected something approaching from the constellation Hercules. At first, it seemed like any other comet, a distant speck of ice and rock following the gravitational pull of our Sun. But the longer they watched, the more questions emerged, quiet peculiarities that didn't quite fit the patterns we've come to expect from objects born in our solar system. They designated it 3I Atlas, the third confirmed interstellar object, and it became the subject of intense observation from telescopes around the world. What made it interesting wasn't any single dramatic feature, but rather a constellation of unusual characteristics that, taken together, created an intriguing pattern worthy of careful scientific investigation. Let's drift through what makes 3I Atlas so curious, taking our time with each detail, allowing the strangeness to settle gently rather than overwhelm. First, there's the matter of its trajectory. When 3I Atlas approached our solar system, It came in on a path tilted just 5 degrees relative to the ecliptic plane. That's the flat disk where all the major planets orbit, the plane that defines the basic architecture of our solar system. Now, for an object arriving from random interstellar space, you'd expect trajectories from all possible angles. Most interstellar visitors should come in steeply tilted, approaching from above or below the plane of the planets. But 3i Atlas arrived nearly aligned with our planetary orbits, moving through the solar system almost as if it knew where everything was. The probability of this happening by chance is roughly 0.2%. Not impossible, but unusual enough to make astronomers pay attention. Then there's where it went. As 3i Atlas moved through the inner solar system, its path brought it unusually close to 3 different planets: Venus, Mars within about 30 million kilometers, and later Jupiter at a distance of 54 million kilometers. This is what some have called a grand tour trajectory, passing near multiple planets in sequence. Again, not impossible through natural dynamics, but when you calculate the probability of a random interstellar object happening to pass this close to 3 specific planets, you get numbers under 0.005%. It's like watching a leaf drift down a stream and seeing it navigate around obstacles, catching eddies that move it precisely where a random leaf wouldn't normally go. It's probably still just a leaf, carried by currents you didn't notice, but it makes you look twice. The James Webb Space Telescope turned its golden eye toward 3i Atlas and performed detailed spectroscopic analysis, breaking down the light reflecting from the object to determine what it's made of. What they found was remarkable: an extreme carbon dioxide to water ice ratio of 8:1, the highest ever recorded for any comet we've observed. Most comets in our solar system have much more water ice relative to carbon dioxide. This extreme composition suggests 3i Atlas formed in an ultra-cold environment, very different from the regions where our solar system's comets were born. It's a reminder that other star systems might have very different chemistry, different formation conditions, creating objects unlike anything native to our neighbourhood. Between July and September, observers noticed something else unusual, an anti-tail phenomenon, where material appeared to be ejected toward the Sun rather than away from it. Comets normally develop tails that point away from the Sun, pushed by solar wind and radiation pressure. Anti-tails are extremely rare and require specific geometric conditions or unusual mechanisms to produce. It's another small puzzle piece that doesn't quite fit the expected pattern. Spectroscopy also detected glowing nickel vapor in the coma, the cloud of gas surrounding the comet's nucleus, but without corresponding iron signatures. This is unusual because nickel and iron typically occur together in natural solar system objects, bound together by the same cosmic processes that formed planets and asteroids. Finding one without the other raises gentle questions about the object's composition and history. Perhaps most intriguing, 3i Atlas showed outgassing activity when it was 6.4 astronomical units from the Sun. That's beyond Jupiter's orbit, much farther than typical comets become active. Most comets wait until they're much closer to the Sun before volatiles start sublimating and creating visible activity. This suggests 3i Atlas contains extremely volatile ices, materials that vaporize at temperatures where water ice remains solid, pointing again to formation conditions very different from our solar system's comet-forming regions. Dr. Avi Loeb, the Harvard astronomer we mentioned earlier in connection with Oumuamua, evaluated 3i Atlas using his own assessment scale for potential technological origin. He ranked it at 4 out of 10, not definitive evidence of anything artificial, but significant enough to warrant serious investigation rather than immediate dismissal. It's an invitation to look carefully, to gather more data, to remain curious without jumping to conclusions. 3i Atlas invites us to practice something valuable, something that extends beyond astronomy into everyday life. It asks us to hold uncertainty with curiosity rather than rushing to conclusions. This object is neither definitively natural nor definitively artificial. It exists in a space of genuine ambiguity, and that ambiguity is scientifically interesting. The universe doesn't always give us clear answers wrapped in tidy packages. Sometimes it presents puzzles that require patience, careful observation, and the willingness to say, "We don't know yet," without feeling uncomfortable about that uncertainty. Learning to sit with not knowing, To observe carefully without premature judgment is a skill worth cultivating. It's the essence of good science, and perhaps good living. We gather evidence, we consider possibilities, we remain open to being surprised, and we wait for more information before declaring certainty. 3. I-Atlas remains a mystery, one we're still observing, still analysing as it moves away from the Sun and back into the depths of interstellar space. Perhaps future observations will resolve the questions it raises, perhaps they'll deepen them. Either way, the watching continues, so 3 I-Atlas remains a mystery, one we're still observing, still analysing, but while we watch visitors from other stars, we might not be alone in watching. There's something else in Earth's orbit, something that appeared at a curious time, keeping pace with our planet in a delicate gravitational dance that no one fully understands yet. While telescopes tracked 3 I-Atlas across the solar system, another discovery quietly appeared in astronomical databases, an object orbiting in lockstep with Earth, and no one's quite sure what it is or where it came from. In August 2025, 2 Spanish astronomers, Carlos and Raúl de la Fuente Marcos, announced the discovery of an object designated 2025 PN7. At first glance it might seem unremarkable, another small asteroid among the countless rocks that populate the space around Earth. But 2025 PN7 is different in a subtle and intriguing way. It's what astronomers call a quasi-satellite, an object that doesn't orbit Earth directly, but orbits the Sun with a period so closely matched to ours that it appears to dance around our planet in the sky, staying nearby without ever being gravitationally bound to us. Quasi-satellites are strange, delicate arrangements. They don't orbit Earth the way the Moon does, instead they orbit the Sun, but their orbital period is almost exactly 1 year, the same as Earth's. From our perspective, watching from the ground, these objects seem to circle around us, tracing looping paths against the background stars. But in reality, they're orbiting the Sun alongside us, their paths synchronized in a cosmic coincidence that can persist for years, decades, or even centuries before gravitational perturbations break the pattern and send them on their way. 2025 PN7 has been in this quasi-satellite configuration since approximately the 1960s, and that timing is curious because the 1960s were when humanity first began launching ambitious interplanetary missions, sending spacecraft to Venus, Mars, and beyond. Many of those early missions failed. Rockets malfunctioned, guidance systems failed, communication was lost, and hardware drifted off into unknown orbits, becoming cosmic debris that we stopped tracking decades ago. Dr. Avi Loeb, along with researcher Adam Hibbert, began investigating whether 2025 PN7 could be one of those lost pieces of human technology. Specifically, they analysed whether it might be the Block L upper stage from Zond 1, a Soviet Venus mission launched on April 2, 1964. Zond 1 lost contact shortly after launch and never completed its mission. The spacecraft itself continued on its planned trajectory toward Venus, but the upper stage that propelled it into space was left in an uncertain orbit, never recovered, never tracked, simply abandoned in the vastness between Earth and the Sun. Using sophisticated trajectory optimization software, Loeb and Hibbert compared 2025 PN7's orbital elements with what Zond 1's upper stage trajectory would have been. The match was intriguing, consistent with the possibility that this object is indeed that 60-year-old relic of the space race. But consistency isn't proof. To know for certain, we need spectroscopy, detailed analysis of the light reflecting off 2025 PN7, to determine whether it's made of metal and composites, like a rocket stage, or rock and minerals like a natural asteroid. We've done this before. In 2020, astronomers discovered an object designated 2020 SE that appeared to be orbiting Earth in an unusual pattern. Spectroscopic analysis revealed it was metallic, and trajectory calculations eventually confirmed it was the Centaur upper stage from NASA's Surveyor 2 moon mission. Launched in 1966 and lost for over 50 years. It had wandered through space for half a century before drifting back into Earth's neighbourhood, a ghost from the Apollo era returning home. Could 2025 PN7 be that lost piece of hardware, quietly orbiting the Sun for 60 years before drifting back close enough for us to notice? As of late 2025, no spectroscopy has been published. The mystery remains open, neither confirmed nor dismissed. There's something haunting about the possibility that pieces of our own history are orbiting above us, forgotten and unidentified. If 2025 PN7 is Zond 1's upper stage, it's a relic of the space race, a fragment of Cold War ambition still silently circling the sun, carrying memories of an era when reaching Venus seemed like the most important thing humanity could do. And if it's not, if it's natural, or something else entirely, that mystery is equally fascinating. Imagine finding an old photograph in your attic showing someone standing in your childhood home. The person looks familiar, but you can't quite remember who they are. They could be a relative you've forgotten, a family friend from decades ago, or even a stranger who wandered into the shot. Until you find more context, the mystery remains, neither troubling nor urgent, just quietly intriguing. And so, Earth might have a companion we didn't know about, quietly keeping pace with our planet for decades. Whether it's our own forgotten hardware or something else entirely, it reminds us that even our immediate neighbourhood holds mysteries. But our tools for solving those mysteries grow more powerful each year, and the network of watchers searching the sky continues to expand. Every discovery we've discussed tonight exists because someone, somewhere, pointed an instrument at the sky and chose to look carefully. Let's appreciate those watchers for a moment, the quiet observers who maintain humanity's vigil, scanning the darkness for signals, movements, patterns that might reveal something new about the universe we inhabit. Modern astronomy is a partnership, a collaboration between massive space-based observatories, professional ground-based telescopes, and a growing community of amateur astronomers equipped with technology that would have seemed miraculous just a few decades ago. Together, they form a global observation network. Thousands of eyes turned upward, each contributing pieces to puzzles that no single observer could solve alone. It's like a vast, distributed conversation where different voices add different perspectives, and gradually, collectively, understanding emerges from the pooling of observations. We've already met the James Webb Space Telescope, that golden eye positioned at the second Lagrange point, peering into the infrared depths of cosmic time, but Webb doesn't work alone. It's part of a constellation of instruments, each designed to observe different wavelengths, different phenomena, different scales of cosmic architecture. The Hubble Space Telescope continues its work in visible and ultraviolet light, providing complementary observations that help astronomers understand objects across multiple wavelengths. The European Space Agency's missions, like the recently launched JUICE spacecraft heading to Jupiter's moons, add their own observations. Even satellites in Earth orbit contribute, monitoring near-Earth space, tracking objects that might pose risks or offer opportunities for study. But increasingly, professional astronomy is being complemented and sometimes challenged by amateur observers who refuse to accept official narratives without verification. In October 2025, Dr. Avi Loeb's Galileo project installed an all-sky camera array atop the Las Vegas Sphere, that enormous spherical venue that dominates the Nevada skyline. The system uses infrared and visible light cameras combined with machine learning algorithms to detect and track anomalous objects in Earth's atmosphere. It's designed to capture what other systems might miss, looking specifically for things that don't behave according to expected patterns. The Galileo project's approach is methodical and transparent. By using triangulation from 3 observatories separated by 10 kilometers, they can determine precise three-dimensional positions, velocities, and accelerations for detected objects. The data is processed openly, with findings published for scientific scrutiny. It's a model of how to investigate unusual phenomena without sensationalism, without predetermined conclusions, just careful observation and honest analysis. And then there are the independent astronomy groups, passionate observers working with modest equipment but extraordinary dedication. The Earth Exists group, mentioned earlier in connection with 3i Atlas, made critical observations that challenged official predictions. When institutional sources suggested 3i Atlas would be too faint and too close to the Sun to observe during its closest approach, amateur astronomers calculated otherwise. They proved it would be visible, and they captured images that confirmed their predictions, demonstrating the power of independent verification. This democratization of astronomy is accelerating. Advanced CCD cameras that once cost hundreds of thousands of dollars are now available for a few thousand software that can automatically detect asteroids, track comets, and measure stellar brightnesses runs on ordinary computers. Citizen science platforms allow anyone with internet access to participate in analysing astronomical data, classifying galaxies, searching for exoplanets, contributing to discoveries that advance human knowledge. The Vera Rubin Observatory, expected to begin full operation soon, will image the entire visible sky every few nights with unprecedented sensitivity. It's predicted to increase our detection rate of interstellar objects by an order of magnitude, potentially spotting dozens per year instead of one every few years. We're entering an era of abundance, a time when cosmic mysteries don't stay hidden for long simply because we weren't looking in the right direction at the right time. There's something deeply beautiful about humanity's collective effort to understand the cosmos. We built machines to see what our eyes cannot, and we share those observations freely, trusting that truth is more valuable than secrecy. Every telescope, whether a multi-billion-dollar space observatory or a backyard instrument assembled by a passionate amateur, participates in the same ancient human impulse, the need to look up and wonder. With these instruments watching, with this network of curious minds recording and analysing, we're building a comprehensive view of the universe that no single observer, no single institution, no single nation could achieve alone. And so, the watching continues. But while we observe distant galaxies and track interstellar visitors, there's another kind of watching happening, another form of listening that has been going on for more than 60 years now. Massive radio telescopes pointed at the stars, receivers tuned to frequencies we think might carry messages, sophisticated algorithms searching for patterns that might indicate intelligence. For more than 6 decades, we've been listening, and for 6 decades the response has been silence. Let's drift into that silence for a moment, into what it might mean, and into the possibility that perhaps we're not listening in quite the right way. The search for extraterrestrial intelligence, known as SETI, began in earnest in 1960, when astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars and listened for signals that might indicate the presence of a technological civilization. He heard nothing unusual, just the natural radio emissions that stars and galaxies produce through ordinary physical processes. But that first search established a methodology, a systematic approach to answering one of humanity's most profound questions. Are we alone? In the decades since, SETI searches have become far more sophisticated. Telescopes scan millions of stars across multiple wavelengths. Computer algorithms process vast amounts of data, searching for narrowband signals, repeating patterns, anything that looks artificial rather than natural. The Breakthrough Listen initiative, funded with $100 million, represents one of the most comprehensive searches ever conducted, monitoring millions of stars and hundreds of galaxies for any sign of technological activity. And yet, despite all this effort, despite all this listening, the universe remains quiet, no confirmed signals, no repeated patterns that can't be explained by natural phenomena, just silence. This silence has a name, the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunch conversation in 1950. The paradox arises from a simple calculation. Our galaxy contains hundreds of billions of stars, many of them older than our Sun. If even a tiny fraction of those stars have planets, and a tiny fraction of those planets develop life, and a tiny fraction of those develop intelligence and technology, there should be millions of technological civilizations in the Milky Way alone. Even if interstellar travel is difficult, civilizations should have had billions of years to spread across the galaxy. We should see evidence of them everywhere: megastructures, radio transmissions, probes visiting solar systems, signs of astroengineering projects. And yet, we see nothing. We hear nothing. The silence is profound. Recent analysis by researchers Manuel Scherf and Helmut Lammer suggests one possible answer to this paradox. They estimate that the nearest extraterrestrial civilization capable of sending probes might be approximately 33,000 light-years away, nearly a quarter of the way across the galaxy. This distance assumes that intelligent technological life is extraordinarily rare, requiring specific planetary conditions that might be uncommon. A planet needs stable carbon dioxide cycles to regulate temperature over geological timescales. It needs plate tectonics to recycle nutrients and maintain geological activity. It needs a strong magnetic field to protect the atmosphere from stellar wind. It needs to orbit a stable star in a relatively quiet region of the galaxy, free from nearby supernovae or catastrophic events that might sterilize the surface. Earth might be rare, a fortunate accident where dozens of independent conditions aligned over billions of years to create a stable platform for complex life. If that's true, then we shouldn't be surprised by the silence. The universe might be teeming with simple life, microbial ecosystems on countless worlds, but technological civilizations capable of sending signals across interstellar space might be vanishingly rare. Perhaps we're one of the first, or one of the few. Perhaps intelligence and technology are evolutionary accidents that don't happen often, or perhaps they happen frequently but don't last long. Civilizations rising and falling on timescales too brief to overlap with others across the vast distances between stars. But there's another possibility worth considering, one that Dr. Avi Loeb has explored in recent years. Perhaps we're searching in the wrong places, listening for the wrong signals, using assumptions that don't match how other civilizations might actually operate. Traditional SETI focuses on radio and optical signals beamed deliberately across space, messages intended to be received. But what if advanced civilizations don't broadcast? What if they send physical probes instead? Small spacecraft that travel between star systems gathering data, observing quietly without announcing their presence. This is the motivation behind projects like the Galileo project's all-sky camera arrays. If technological artifacts are visiting Earth's vicinity, either as autonomous probes from other civilizations or even remnants of our own space programs drifting in unexpected orbits, we need to look for them directly rather than waiting for radio signals. It's a shift in methodology, from passive listening to active observing, from expecting deliberate communication to searching for physical presence. The implications are profound. If even one unambiguous technological artifact of non-human origin were confirmed, it would transform our understanding of our place in the cosmos. We would know with certainty that we're not alone, that intelligence and technology have emerged elsewhere. It wouldn't answer all questions, it would raise countless new ones, but it would fundamentally change the conversation. From are we alone to what are they like? What can we learn from them? How should we respond? But until such confirmation arrives, the silence remains, and in that silence, we're free to imagine possibilities, to dream about what might be out there, to consider the extraordinary patience required to search for something that might not exist or might be so different from us that we wouldn't recognize it, even if we found it. The universe is vast, incomprehensibly vast, and we've only just begun to look carefully. Perhaps the silence is simply because we're still learning where and how to listen. Perhaps the answer is waiting just beyond the edge of what we've explored so far, in the next dataset, the next observation, the next object that catches a telescope's attention. Right now, as you lie there, radio telescopes around the world continue their vigil. Software algorithms continue analysing data streams, searching for patterns in the cosmic noise. The listening continues, patient and methodical, driven by curiosity and the hope that someday, perhaps tomorrow, perhaps in 100 years, the silence will break. And so, the search continues. We watch the sky, we listen to the radio whispers between stars, and we build instruments capable of detecting things our ancestors couldn't imagine. But while we search for intelligence beyond Earth, perhaps we should also appreciate the extraordinary structure that holds everything together, the vast cosmic architecture within which all of this searching and wondering takes place. Let's drift outward now, pulling back from individual stars and galaxies to see the universe at its larger scales, where matter organizes itself into structures so immense they challenge comprehension. If you could step outside the universe and view it from a distance impossible to achieve, if you could see all the galaxies at once spread across billions of light years, you'd notice something remarkable. Galaxies aren't scattered randomly through space like stars scattered across the night sky. Instead, they organize themselves into vast filaments, sheets, and clusters separated by enormous voids where almost nothing exists. The universe has structure, a cosmic web that emerged from the nearly smooth distribution of matter in the early universe and grew, over billions of years, into the largest patterns nature has ever created. This structure is called the cosmic web, and it's one of the most successful predictions of modern cosmology. Computer simulations run in the 1980s and 1990s predicted that dark matter, the invisible substance that makes up most of the matter in the universe, would clump together under gravity in a specific pattern. Dense filaments would form where matter flows together, creating highways of galaxies. Where multiple filaments intersect, enormous clusters would grow, containing thousands of galaxies bound together by mutual gravity. And between these filaments and clusters, vast voids would stretch across hundreds of millions of light years, nearly empty regions where very few galaxies formed because the initial density of matter was too low to trigger significant gravitational collapse. When astronomers mapped the actual positions of millions of galaxies using large surveys like the Sloan Digital Sky Survey, they found exactly the pattern the simulations predicted. The cosmic web is real, observable, and remarkably consistent with theoretical expectations. It's one of the great triumphs of cosmology, proof that we understand, at least in broad outline, how the universe grew from simplicity into complexity. The largest structures in this cosmic web are galaxy superclusters, regions where hundreds or thousands of galaxy clusters group together across distances of several hundred million light years. Our own Milky Way galaxy belongs to the local group, a small cluster containing the Milky Way, Andromeda, and about 50 smaller galaxies. The local group, in turn, is part of the Laniakea supercluster, a structure containing approximately 100,000 galaxies spread across 520 million light-years. Laniakea is Hawaiian for immeasurable heaven, and the name captures something of the scale involved. To cross Laniakea at the speed of light would take 520 million years, a journey spanning timescales far longer than complex life has existed on Earth, and Laniakea itself is just one supercluster among countless others, all part of the larger cosmic web that fills the observable universe. Within this web, matter flows along gravitational currents like water flowing through river systems. Galaxies don't simply orbit within their clusters, they stream along filaments, following paths determined by the distribution of dark matter that dominates the gravitational landscape. Our local group is actually moving through space at about 630 kilometers per second, carried by these large-scale flows toward a region astronomers call the Great Attractor, a gravitational anomaly hidden behind the plane of the Milky Way, but massive enough to influence the motion of thousands of galaxies across hundreds of millions of light-years. Beyond the Great Attractor lies an even larger structure called the Shapley Supercluster, one of the most massive concentrations of galaxies in the nearby universe, containing more than 8,000 galaxies. The combined gravitational pull of these structures shapes the motion of everything in this region of the universe, including us. We're not stationary observers watching a static cosmos. We're travelers, moving through space at extraordinary speeds, carried by gravitational currents we've only recently learned to map and understand. The voids between these structures are almost unimaginably empty. The Bhuta's Void, discovered in 1981, is a roughly spherical region about 330 million light-years across, containing only about 60 galaxies where we'd expect to find thousands. Most of that volume is just emptiness, intergalactic space expanding without interruption, containing perhaps a few stray atoms per cubic meter, but otherwise vacant. To cross a void like Bhuta's, even at the speed of light, would take hundreds of millions of years, travelling through darkness so complete that you'd see almost no stars, no galaxies, just the faint glow of the cosmic microwave background radiation filling all of space. These voids grow larger as the universe expands. The space between galaxy clusters is stretching, driven by dark energy, that mysterious component of the universe that causes the expansion to accelerate. Eventually, over timescales of hundreds of billions of years, the cosmic web will be pulled apart. Galaxy clusters will become isolated islands, separated by such vast distances that light from one cluster will never reach another. Each cluster will appear to be alone in an empty universe, the cosmic web dissolved by expansion into disconnected fragments. But that's a future so distant it's barely imaginable. Right now, in this era, we live at a time when the universe is filled with structure, when galaxies organize into beautiful patterns we can observe and study. We exist during what future cosmologists might call the golden age of astronomy, when light from distant galaxies can still reach us, when the cosmic web is visible and mappable, when the universe's past is written in the light of ancient galaxies still arriving after journeys lasting billions of years. There's something remarkable about this moment in cosmic history. We're conscious beings, collections of atoms organized into patterns capable of thought, and we've emerged at a time when the universe is old enough to have formed stars and planets and life, but young enough that we can still see the evidence of its beginning. The cosmic microwave background radiation, that faint glow from the Big Bang, is still visible. The most distant galaxies formed when the universe was young are still within reach of our telescopes. We're perfectly positioned in time to understand our origins, to see where we came from and how we got here. And so, the cosmic web spreads across billions of light years, a structure so vast it contains everything we can observe, every star, every galaxy, every distant quasar shining from the early universe. It's the largest pattern nature has created, and we're part of it. Tiny observers on a small planet orbiting an ordinary star within one galaxy among hundreds of billions, yet somehow capable of comprehending the whole magnificent structure. Let that settle for a moment. You're lying there, breathing slowly, thinking about structures spanning billions of light years, about galaxies streaming along filaments of dark matter, about voids so empty they contain almost nothing for hundreds of millions of light years. And all of this exists right now surrounding us, holding us within patterns we're only beginning to understand fully. It's extraordinary that we can know these things, that consciousness emerged in this universe and developed the capacity to map its own cosmic context. From atoms arranged into thinking matter on one small planet, we've built instruments that see across the observable universe, we've developed theories that explain the larger structures, and we've created maps showing our place within the whole. But now let's bring ourselves back, drifting down from those cosmic scales to something closer, something more intimate. Let's return to Earth, to this moment, to you lying there thinking about all of this, because perhaps the most remarkable mystery isn't out there in distant galaxies or ancient light. Perhaps the most remarkable mystery is that the universe produced something capable of wondering about itself. And so we've travelled from the most distant galaxies, formed when the universe was barely born, to interstellar visitors passing through our solar neighbourhood, to objects orbiting alongside Earth that we can't quite identify, to the vast cosmic web that holds everything together across billions of light years. We've looked at instruments built to see what our eyes cannot, at the silence of space where we expected to hear voices, at structures so immense they contain hundreds of billions of galaxies. And through it all, there's been an observer present, someone experiencing all of this information, processing these ideas, imagining these vast distances and ancient times. That observer is you. Right now, as you lie there, perhaps in darkness, perhaps with soft light filtering through a window, you're made of atoms forged in the cores of dying stars that existed billions of years ago. The carbon in your cells, the oxygen you're breathing, the calcium in your bones, the iron in your blood, all of it was created through nuclear fusion in stellar cores and scattered into space when those stars died. You are, quite literally, made of stardust, atoms that have existed for billions of years, cycling through generations of stars, drifting through interstellar space, eventually coalescing into the solar nebula that formed our sun and planets 4.5 billion years ago. Those atoms became part of Earth, cycling through geological processes, eventually incorporating into the biosphere when life emerged. They've been part of countless organisms over hundreds of millions of years, recycled through ecosystems, transferred from soil to plant to animal and back again. And now, for this brief moment in cosmic time, they are arranged into the pattern we call you. Conscious, aware, capable of thinking about their own origin and wondering about their place in the cosmos. The probability of your existence is vanishingly small when you consider all the conditions that had to align. The universe had to have precisely the right fundamental constants for stars to form and for chemistry to be possible. The Big Bang had to produce the exact ratio of matter to antimatter that allowed normal matter to survive. The early universe had to have tiny density fluctuations that eventually grew into galaxies and stars. Our galaxy had to form in a region stable enough for stars to live long lives. Our sun had to be the right mass, in the right location. Forming with the right distribution of elements, Earth had to orbit at the right distance, with the right size, the right atmosphere, the right magnetic field. Life had to emerge and survive countless extinction events. Evolution had to follow a path that led to consciousness, to intelligence, to you. At every step, things could have gone differently, and yet here you are, the product of an unbroken chain of events spanning 13.8 billion years, tracing back to the first moments after the Big Bang when space and time themselves came into existence. You are the universe experiencing itself, matter arranged in such a way that it can contemplate its own nature. That's not poetic exaggeration. That's simply what's happening. The atoms that make up your brain, forged in ancient stars, are now configured to process information about those very stars, about the processes that created them, about the vast cosmos they inhabit. There's something almost miraculous about consciousness emerging in a universe that seems, at first glance, so indifferent to life. The cosmos operates according to physical laws that care nothing for survival or meaning. Stars burn not because they choose to, but because gravity compresses their cores until nuclear fusion ignites. Galaxies collide not with intention, but because gravity pulls them together over billions of years. The universe expands not toward any goal, but simply because that's what space-time does, following the equations that govern its behaviour. And yet, within this apparently indifferent cosmos, on at least one planet orbiting one star, among hundreds of billions, complexity increased to the point where matter became self-aware. Simple molecules became complex molecules, became self-replicating molecules, became cells, became multicellular. Organisms became creatures with nervous systems, became beings capable of abstract thought, of language, of science, of looking at the night sky and asking, what is all of this? Where did it come from? What does it mean? Perhaps we're rare. Perhaps Earth-like planets with stable conditions lasting billions of years are uncommon. Perhaps the emergence of life requires such specific chemistry that it happens only on a tiny fraction of suitable worlds. Perhaps the evolution of intelligence is a fluke, an accident that occurred here but might not occur elsewhere, even given billions of years and countless planets. If that's true, if we're among the few or even the only conscious observers in this galaxy, then we carry a profound responsibility to observe carefully, to understand deeply, to preserve the knowledge we gain, because we might be the universe's only way of knowing itself in this region of space and time. Or perhaps we're not rare at all. Perhaps consciousness is common, emerging on countless worlds throughout the galaxy, throughout the universe, taking forms we might not recognize as conscious because they think in ways so different from ours. Perhaps right now, on planets orbiting distant stars, other beings are lying in their equivalent of beds, thinking about the vastness of space, wondering if they're alone, looking at their night sky and seeing constellations we'll never know, asking the same questions we ask but in languages and concepts we couldn't begin to comprehend. Either way, whether we're rare or common, the fact remains that you exist. Against odds that seem almost impossible, through a chain of events spanning billions of years, matter organized itself into a pattern capable of experiencing the universe. And that pattern is having an experience right now, in this moment, thinking these thoughts, feeling whatever you're feeling, existing in a specific place at a specific time in the history of the cosmos. This moment will pass. Tomorrow you'll wake up and return to your daily concerns, to the immediate and practical demands of living. The distant galaxies and ancient light will fade from your thoughts, replaced by schedules and conversations and tasks that need completing. And that's okay. That's necessary even. We can't live every moment in contemplation of cosmic scales. We have lives to live, relationships to maintain, work to do, challenges to face the mundane matters, because it's where we actually exist, where our actions have consequences, where meaning emerges through connection with other conscious beings, but perhaps occasionally, on clear nights when you see stars through your window, or in quiet moments when your mind wanders, You'll remember what we've explored together tonight. You'll remember that the light touching your eyes from distant stars began its journey years or centuries ago. You'll remember that interstellar visitors occasionally pass through our solar system, carrying stories from places we may never reach. You'll remember that we're part of a vast cosmic web, connected through gravity and shared origin to everything else in the observable universe. You'll remember that you're made of atoms forged in stellar furnaces, that you're the universe experiencing itself, that consciousness is perhaps the most remarkable phenomenon that matter has ever achieved. And maybe, in those moments of remembering, the concerns that seemed overwhelming will find their proper proportion, not because they don't matter, but because they matter within a larger context, a cosmic perspective that holds both the immediate and the eternal, both the small and the vast, both the personal and the universal. Problems don't disappear when you contemplate billions of light years, but they can transform, becoming challenges to face rather than insurmountable obstacles, temporary difficulties within a longer story that continues beyond any individual struggle. The universe is vast and we are small, but smallness doesn't mean insignificance. Perhaps significance isn't about size or duration. Perhaps it's about experience, about consciousness, about the capacity to wonder and create meaning, even when the cosmos itself offers no inherent meaning. We are brief arrangements of atoms, yes, but we are arrangements that can contemplate their own existence, that can build telescopes to see across billions of light years, that can develop theories explaining the structure of space-time itself, that can create art and music and poetry celebrating the strange beauty of being alive in a universe that didn't have to produce life at all. The stars will continue burning whether we observe them or not. Galaxies will continue their ancient dance through space. Regardless of whether anyone maps their movements, the cosmic web will persist long after humanity has vanished if we are destined to vanish. But right now, in this moment, observers exist, you exist, and that existence, however brief in cosmic terms, is remarkable. You are the way the universe knows itself, even if only for a moment, even if only partially, even if your understanding is limited by the constraints of human cognition and the technology available in this era. Every question we've explored tonight remains open. We don't know for certain whether 3i Atlas is natural or something else. We don't know what 2025 PN7 truly is. We don't know why Webb discovered those impossibly bright early galaxies. We don't know whether we're alone or part of a galaxy filled with conscious observers. We don't fully understand dark matter or dark energy, or the ultimate fate of the universe. And that's beautiful in its own way. Mystery isn't the absence of knowledge, it's an invitation to continue exploring, to keep looking, to remain curious about the nature of reality. The search continues. Telescopes scan the sky, algorithms process data, researchers analyze observations and develop new theories. Amateur astronomers contribute their own findings, and gradually, piece by piece, the picture becomes clearer, even as each answer reveals new questions waiting to be asked. So let yourself drift now. You don't need to remember every detail we've explored tonight. You don't need to hold on to the numbers or the names or the specific observations. Let them wash over you like gentle waves, present for a moment and then receding, leaving only a quiet sense of wonder about the universe we inhabit together. As you lie there, breathing slowly, feel the weight of your body against whatever surface supports you. Feel the rhythm of your breath in and out, that same oxygen cycling through your lungs that has cycled through countless living things before you, that was created in stars billions of years ago and will continue existing long after this moment has passed. The universe is vast and you are part of it, not separate from it, not an observer standing outside looking in, but woven into its very fabric, made of the same substance as stars and galaxies, subject to the same physical laws, connected through space and time to everything that exists. And in this moment, that's enough. You don't need to solve the mysteries tonight. You don't need to understand everything. The cosmos will still be there tomorrow, still vast, still mysterious, still beautiful. The questions we've explored will continue being investigated by dedicated observers around the world, adding pieces to puzzles that may take generations to complete. For now, just rest. Let your mind settle. Let the thoughts drift like distant galaxies, beautiful and mysterious and infinitely far away. Let sleep come gently if it wants to come, or let wakefulness hold you softly if that's where you are. Either way, you're exactly where you need to be, a small part of something vast, a brief moment of consciousness in a universe that has been unfolding for 13.8 billion years and will continue long after this night has ended. The stars are still shining out there in the dark, the galaxies are still spinning through space, light is still travelling from distant places toward observers who might see it someday. The cosmic dance continues, patient and eternal, and you're part of it, right here, right now, in this quiet moment. Thank you for spending this time together, exploring the mysteries of the distant and the near, the ancient and the immediate, the vast and the personal. May these thoughts bring you peace rather than restlessness, wonder rather than anxiety, connection rather than isolation. Good night. Rest well, and remember, when you look up at the stars, you're seeing light that travelled for years or centuries just to reach your eyes, connecting you across time and space to places beyond imagining. You are the universe looking at itself, and that is a beautiful thing to be. Good night.